Welcome to this tutorial of the Kratos ROM application. This is the 9th tutorial of the series, and in this one we continue talking about ROM advanced options with ROM Manager. The example that we will be launching is the fluid dynamics example, so these are the requirements. We will be discussing Galerkin and LSPG and Petrov Galerkin, which are our different projection strategies available as of now. Before doing that, let me just recall from last time these decoders that we have in Kratos. It is the linear decoder that is simply multiply phi times q, this little vector I'm calling q, and the nonlinear decoder, which is multiplying phi times q plus another phi, which is phi inf and phi sup times the product of the whatever I get from the neural network when I input q to the neural network. So this is a nonlinear decoder, and that's a linear decoder. And that's what we saw last time. Now the question is simply what is the derivative of that decoder applied to Q with respect to Q. For the linear case, it's trivial. It is simply phi. So phi is a matrix with this dimension, number of degrees of freedom times n. And for the nonlinear decoder, it is a little bit more convoluted, but let us simply state it as V. And V is a matrix that is of dimension, a very similar dimension, number of degrees of freedom times n inf, which is the dimension of the linear part of the decoder, let's say. So in the following slides, I had the slides only for the linear case, but if we change phi in the following slides by v, we'll be taking into account also the nonlinear case when our decoder, let's say, is nonlinear. So that's the only note that I wanted to start with. In the following slides, either just in order to take into account a nonlinear decoder, then let's change just phi by this v. Okay, let's see then the Galerkin, LSPG, and Petrov Galerkin. So this is a representation of the linear system of equations that is solved on every nonlinear iteration. So we have a Jacobian on this side, we have the residual on that side, and we just solve for an increment, and then until we do this until we converge. The system is of dimension number of degrees of freedom by number of degrees of freedom. What we do when we apply a Galerkin method is that we apply a projection, so we post multiply this left hand side matrix by phi. Of course, here instead of phi, if your decoder is nonlinear, you would put v, the one that we saw. And also we pre-multiply both left and right hand side by the phi transpose. If you do this, you will see that this product results in a matrix of dimension capital N by capital N, and this on a vector of dimension n, capital N, I mean. So this is a system of dimension 10 by 10, let's say. It's a very small system. That's a gaining on using the Galerkin method or any of these methods, that the system in the end will be very small. So in Galerkin method, basically we post and pre-multiply by the same matrix. In the others, they have the PG, that stands for Petrov Galerkin, which somehow points to the fact that we are going to pre-multiply and post-multiply by different matrices. In this case, the first one is LSPG. This is the scientific paper that describes it in more detail, but basically what it does is we pre-multiply by these phi transpose J transpose. Here also phi transpose J transpose. So pre-multiply by this matrix. Of course, phi transpose would be V transpose if it is a nonlinear decoder. But this that we are pre-multiplying is different from what we are post-multiplying here, so that's a Petrov Galerkin part. The LS, least squares, comes from some optimality properties of this method, in particular for problems in fluids. So for problems in fluids, for problems in which this matrix J is non-symmetric positive definite, so not SPD, so not SPD. For example, Galerkin method works well for structures where matrices tend to be symmetric positive definite, and this one was proposed for fluids in which this is not the case. So the last one that we have in Kratos is this one. We have a fixed matrix psi on here, which is of course different from the one that we are having here. If we are, again, on a nonlinear decoder, we would have here a V. But this is the Petrov-Galerkin. This is a method that was proposed by our group. You can follow the link for the scientific reference. And that is the way, basically, in any of the three cases, how we compute this little vector Q, let's say. And from that little vector Q, we can decode it in any linear or nonlinear fashion. So that's all the theory I wanted to mention. And now let's see how we set this in an example. In this case, in the fluids example, let's go to the main Kratos.py and let us. This is the last example that we launched. Let me just comment this here, and ROM Manager .print errors, and let us launch it. Of course, I didn't errors. So this one was launched last time, so from the database it should just be retrieved 3.47 e to the minus 5. The default projection strategy is the Galerkin strategy, so you have come here. So let me just copy this line from the defaults in the ROM Manager. So I will paste it in the main field here, and oops, I actually had pasted already. So Galerkin is the one that we had already used. I mean, if we don't have anything, that's the default. Let us put LSPG. So LSPG, as we said, will use the same basis matrix that we computed from the SVD. And you see we're not launching the full order model because the basis phi is the same that we have available. We just use it in conjunction with the J matrix on every iteration, and we get this error. So let us go then for the Petrov-Galerkin. The Petrov-Galerkin, if we inspect this data, ROM data folder, there is only right basis matrix. We can expect this psi matrix to be stored there for the Petrov-Galerkin. Let us go here. I will just paste this here, Petrov-Galerkin. And when it reaches 50, let's see the error. In this, we just saw that it launched something there, and what it was doing, it was computing the left basis matrix. Now we have this right basis matrix, which is our phi, and we have our left basis matrix, which is our psi. So now the error is it's very similar to the LSPG, and that's not a surprise because our Petrov-Galerkin, the way it is implemented in Kratos, it is approximating the LSPG, but with a fixed matrix rather than a changing one. Changing because this J changes on every nonlinear iteration. Therefore, kind of the space in which you project also changes on every iteration. In contrast here, this is a fixed space. It is just a matrix psi. Well, that's how you set it up. There are some, we come to the ROM Manager, there are some parameters. For example, here you have specific parameters for Galerkin, for LSPG, and for Petrov-Galerkin. For the case of Petrov-Galerkin and Galerkin, you will see that you have this monotonicity preserving only. This is probably we will be erasing this. This is very specific for one of the cases in which you have instabilities. For you, it will be okay to just keep it as false all the time. We might deprecate it soon. And for LSPG, you have more options. So these options are related to the fact that the LSPG is used for training the Petrov-Galerkin. So we said that I just mentioned that Petrov-Galerkin is an approximation of the LSPG, and therefore you need to first launch some examples of LSPG, and then you can get your right basis matrix. And this, whether you use residuals, here are the options, residuals, Jacobian, or reactions here, what is tolerance for an SBD, internal SBD. So this is very particular for getting this fixed psi matrix that is used in LSPG. So those are the parameters that are listed here. That's it. That's what I wanted to cover in this tutorial. So we saw the different projection strategies. So Galerkin is the most usual for structures. LSPG is proposed for fluids, although you saw that for this particular flow path cylinder, we were getting better results with the plain Galerkin, and then the Petrov Galerkin was similar to LSPG because it is an approximation to it. In the following tutorial, in the last one, we will be covering the ROM. That is a way of making our reducer models even faster.